Hello, in this video we are going to continue our discussion in Algebra 2 about our linear equations. We're going to finish up this week discussing linear models. This is Chapter 2, Section 5. Our objectives here are to write linear equations that model real-world data, and we are going to try to make predictions from the linear models or linear equations that we create. In order to do so, we need to be familiar with certain vocabulary terms, scatter plot, line of best fit, as well as the numerical value that we apply to how well a line fits a group of data. We call that the correlation and the correlation coefficient. So to get started, we'll start off by saying that graphs of data pairs in real-world situations rarely fall in a perfect line. In fact, it's pretty unusual, it's very unusual for data points obtained from real-world observations to fit perfectly in a straight line. But their arrangement can suggest a relationship that you can model closely with a linear function. So even though they may not be a perfect fit, a line could be pretty close to what the data suggests. So these pictures down here, all of these dotted points represent real-world data that's been collected and placed on a graph, and we call that graph a scatter plot. In each of these graphs, we relate two sets of data, an input value and an output value, a domain and a range coordinate, if you will, from our ordered pairs. And we use this scatter plot to determine the correlation between those two data sets. So what's the correlation between the input values and the output values? We describe these relationships using some simple terminology. It's not 100% clear where some of these terms come from or when to use them. It's kind of a judgment call on your part, but these are some of the terms that we end up using to represent the following data. In this case, we could imagine that there's a downward straight line going through these data points, and the data points are fairly close to that line. So we would say that there's a strong correlation to this line, and because the slope of this line appears to be negative, we would call this a strong negative correlation. In this next example, again, it appears to me that the data points are grouped in a line, and that line has a downward slope, but the data points this time are not as close to this line. So while I would still say that this has a negative correlation, I think I would suggest that this is called a weak negative correlation. And this is why I was saying the terminology sometimes isn't that precise. What one person describes or defines as a strong correlation might be another person's weak correlation, and so on. But I think in this case I'd be happy if you identified this one as a strong correlation and this one as a weak correlation. Now, if there doesn't appear to be any sort of pattern in the data, if they truly are scattered with no pattern to them whatsoever, we would say that there's no correlation between the input and output values. And similarly to the first two, these last two have a weak correlation and I would say a strong correlation, but the difference here is that they have positive correlation because of the slope of the line being positive. So in order to observe examples of this in the real world, that's kind of our main goal for this video, we need some data points. So in this next example, we're going to use some information from somebody's electric bill. We see what the average temperature was given in a given month, and we can see what the cost for electricity was for that month. So in another month, we have a different cost, and so on. So I'm going to ignore the names of the months as far as inputs and outputs go, and I'm going to treat my average temperature as an input value, and I'm going to call the electricity bill the output value. So we have ourselves domain and range components, and we have looks like 12 months of data, so these two tables actually go together as one. So we're going to use a graphing calculator from our classroom or installed on your computer to create the scatter plot, and I'm going to show that to you right now. So in just a few quick moments, we can actually take the data from our paperwork here and place them into the calculator. So I'm going to model that here, and then in a minute I'll write down the rules and the procedures for you to try this on your own. So first thing that we're going to do is we're going to turn our calculators on and press the on button until we get to this home screen. We're going to choose a new document. If you're prompted to save, I would say no, don't save, and just create a new document. Instead of adding a calculator or graphs page like we have already in class, we're actually going to add a list and spreadsheets page. This will allow us to enter data points into the table for which we can perform our analysis. Now before we go too far, we need to label our data points. So for our input column, I'm just going to write temperature for average temperature. I should say I'm writing temp abbreviated. And then in the second column, I'm going to type bill for the electricity bill. And we skip this line. This is a spot for us to write an actual equation to generate data points. Since we have all of the data points, we'll just type them in here. Now I'm just going to go through and add each of these data points by typing in the number and pressing Tab or Enter to move around the screen. I can also use my arrows as well. So this is a bit time consuming if you're using the handheld calculators. Hopefully we have an opportunity to download the software onto your computers and it goes much faster. So I think you get the idea. I'm going to pause the video now and fill in the rest of the data points. Okay, so I've made it to the bottom of the data set, and a quick check shows that I do have 12 data points. I have an input and an output value for each one. So the next thing that I'm going to do is press this control button and our doc button. This will add a new page to our document. Each one of these tabs is a page in our software. So if I press control doc, that adds a new page, and we can add another page to our document here with a calculator or a graph, etc. It may be tempting to use graph this time, but we're actually going to create a graph using this, a data and statistics page. This will give us the opportunity to perform an analysis with our data next. So if I click the data and statistics page, we now have coordinates or ordered pairs for each of the rows that I've entered on the list and spreadsheets page, but there's no organization to this whatsoever. So this data point and this data point, they're just randomly placed on the screen. There should be some order to this, and we can show that by defining our variables on the bottom and the side axis. So again, a minute ago I said that our temperature is going to be our independent variable. So I'm going to click on the x-axis here to add a variable. This is our input or independent variable. So I'll click temperature for that. And you can see my data points start to fall in line. I could also click on this left side and specify that the bill, the dollar amount from it, is our dependent variable. And so if you see these points plotted now, I think we can all agree that there is a positive correlation. The line that goes through these data points, or that is close to these data points, does have a positive slope. But the question becomes, is this a strong positive correlation or a weak positive correlation? And if we just look at this window, I think I would accept either one. I think you can make the argument for either or. But I'd like to show you something else. If we click our menu and adjust our window, let's change our window to show our minimum X value and minimum Y values to be 0. So I'm just going to type 0 here and 0 here. This will allow our graph to start at the origin. I think I'm going to leave the X maximum and Y maximum alone. So now we can see when temperature is 0 and our bill is 0. That part fits on our data. Or I should say we can see our data in that scale. Now it looks to me like these data points are clustered a bit tighter to one another when I look at the whole picture. So if it were me, I would probably suggest that this has a strong positive correlation. But again, if you want to make the argument that this is weak based on the first picture that you saw, I'd be okay with that. And I think the biggest takeaway is that we all agree that this is some sort of positive correlation. So the line of best fit is also known as a trend line. and it's the one that approximates the relationship between these variables or the data sets. Of course, our calculator can help, and sometimes we call this the line. Oops, let's try to fix that here. The line of best fit. And you'll see the phrase or the term regression analysis or just regression in our calculator setting, and that means the same thing. And we're going to use that line of best fit or the regression to make our predictions from the data. So there are a few steps, I think about 6 of them. So I'll go ahead and write them down here, and we'll try to walk through that process again with another example. So if you recall, the first thing that we did is we created a new document, and we created a page within that new document called a list and spreadsheet. That was option number 4. From there, we placed titles across the top of our screen for the names of our input and output variables, and then we took the time to enter our data. We typed in the results for both the X and the Y columns. After that, we pressed the Control and then Document buttons. I'll put those in boxes here so we remember that those are buttons. We pressed the Control and Document buttons to add a page, and when we added the page, we specified that it should be a data and statistics page, and that was option number 5 when we made that selection. From there, we specified the variables on each axis. So this is where we clicked on the bottom side of the screen and the left side of the screen in order to place our variables down here at the bottom or on the left-hand side. Now in our last example, I did adjust the window, but that's not always necessary. In fact, it's not necessary at all for the next 2 steps. These next 2 steps tell us how to find our line of best fit, or the regression line. So what we're going to do is we're going to press the menu button. We're going to choose option 4, then option 6, and then option 1 for a linear regression. So let me show you that. Our menu button, we press option number 4, that's to analyze our data. Then we slide over and choose option 6, that will create a regression that fits our data. And in other classes we might consider these other options, but for us we're interested in the linear equations. And in our class specifically, we are more familiar with the slope-intercept form of a linear equation, so we'll choose mx plus b. And there you have it. Here's an equation that shows the linear equation that most closely fits the data. Now, depending on who used your calculator last, since these are shared in the classroom, this last option may not be turned on for you. It was on my screen, but I'll show you the difference here. If you press menu 8 and choose the diagnostics option, that will display our R-squared value, and this is essentially our correlation number. So let me show you what I'm talking about. This R-squared number is our correlation value. If I press menu, choose option 6 for settings, and then check or uncheck this box, that'll display the R-squared value or not. Now, in most of the classes that I teach, I like having that diagnostics value there, the R-squared value there, so that we can see how well our data fits the line, or vice versa, how well the line fits the data. Also, while we're here, it might be worth noting that we can adjust how many digits are on display for our calculator on this screen. If I revert this back to auto, the default option, sometimes we'll see that our decimal points run off the screen, and it's a little bit hard to interpret. So if we're in the settings option and we change this from auto to something like float 3 or float 4, that'll give us a more meaningful result. And here we have it. For this particular equation, we have a linear equation. For this particular data set, we have a linear equation of 4.15x minus 118. So there's the equation that fits the data that we have. When our input is the temperature for the month, our output will be our electricity bill. We can use this equation to predict that cost. So we're going to use these 6 steps, and I'm going to challenge you to try the next part of the assignment on your own. We have another set of data on the second page, and I would like for you to find the line of best fit for the relationship between calories and fat that are found in fast food hamburgers. We're going to treat our calories as the independent variable, or input value, and we'll choose our grams of fat as our output value. I would recommend pressing the home button on your calculator to create a new document, and don't save your work from the last one. And from there you can begin the procedure again. Start with list and spreadsheets and create your data. So I'm going to pause the video now and resume playback in a moment with my information on the screen. I would like for you to do the same and create the line of best fit on your own using the steps from above. Okay, so in this case, if we had a column for calories and a column for the grams of fat from each hamburger, we have about 9 data points, and we can plot them and find the line of best fit. So here we go. It looks like we have a linear equation and a residual, or an R-squared value of 0.897. So we'll use this equation to make a prediction in part B of our work. We had y equals 0.071x minus 9.27. So with x as our input value, the number of calories that are found in a particular hamburger, the y result should be the approximate grams of fat in that hamburger. So by using this equation, we can now make a prediction. What if we had a 330 calorie hamburger in front of us? How much grams of fat would it likely have? Well, if we take the equation 0.071 and multiply it by 330 for the calories in the hamburger, then this calculation here should produce the amount of fat in grams that we would expect to see in this particular hamburger. Now, I did use my calculator off screen to obtain this result. I trust that you could do this on your own too. This value comes out to be 14.16 grams. So if we're going to have a hamburger that has 330 calories to it, we can expect that we would be intaking about 14 grams of fat. And the last example, or last part of this example, is illustrates a good reason why we like to have an equation that fits this data. To answer this question based on just the examples that we've seen here, and even just looking at the graph might be kind of hard to interpret. So the question is essentially, which is more unreasonable? Which one of these doesn't seem to make sense? If I had a 200-calorie hamburger, should it have 10 grams of fat? Or does a 660-calorie hamburger have 36 grams of fat? Well, if I look through the data that I have here, I don't have a hamburger that has 660 calories to compare to, and I don't have a hamburger that has 200 calories to compare to. So I might look at the graph here and look around. I almost didn't catch this one. I didn't realize we did have a data point that was remarkably close to 600. So this data point here, 598, almost 600, this particular hamburger had 26 grams of fat. We can see that it's below the trend line. It's pretty far away from the expected value. So that seems a bit unusual to me. What I would recommend is using our calculator here. And the equation that we just established. This trend line predicts what our results ought to be. And so if I said, well, if I took the 0.071 and multiplied it by 660, and subtract 9.27 from it. This is going to give us our predicted value, or the amount of grams of fat for that particular hamburger. And according to our line of best fit, the expected amount of fat in that hamburger would be about 37.6. So not too far off of our 36 gram. Let's see what the next calculation comes out to be. What if we evaluate this 0.071 times 200 minus 9.27? What do we get there? Well, that one comes out to be about 4.9 grams of fat. Okay, this was grams of fat. So which one of these appears to be less realistic? 10 grams of fat for a 200-calorie hamburger, or 36 grams of fat for a 660-calorie hamburger? Well, if it were me looking at it, I would note that the 37 grams predicted from our line of best fit is awfully close to the 36 grams of fat, whereas the 4.9 grams of fat predicted for a 200-calorie hamburger is awfully far from the 10 grams. So which one is not reasonable? I would argue that this one is not reasonable, and we can explain further with the equation that we just described. So to finish out this video and to wrap up this week, I would like for you to complete these review questions on your own. I think with a general understanding of linear equations and the examples that we've practiced so far this week, you should handle these on your own. Please pause the video now and try them, and in a few moments you can resume playback to check your work. Okay, so here we have it. In problem number 1, effectively we're finding the slope of a linear equation, and you may not have recognized it at first, but we kind of are. If we have time as our independent variable and distance as our dependent variable, we could take the rise in our dependent variable and divide it by the run of our independent variable. Shauna drives 75 miles in 3 hours time, so that means that she's driving about 25 miles per hour on average. And if she drives 25 miles per hour for 2 hours, then that means that she travels a total distance of 50 miles in 2 hours. In the next 2 examples, we were asked to write the equation in slope-intercept form. Remember, that's y equals mx plus b. And our whole goal here is to get the y value by itself. So if we had this problem originally given to us in question A, and our job was to get y by itself, first thing we do is to move the 5x to the other side by subtracting 5x from both sides of the equation. Then we can move this -4 to the other side of the equation by dividing both sides by -4. Keep in mind here that this -4 divided both pieces, the 5x and the 3. And that leaves us with -5 divided by -4, which is just going to be reported as 5/4 positive, times x, and positive 3 divided by -4, we'll just call that a -3/4. In part B, again, reminder, we're talking about mx plus b. That's our slope-intercept equation. We were told the slope was 0 and the intercept was 2. But I wanted to show you this example or revisit it because if we recall, 0 times anything is just 0, and 0 plus anything is that original number, that anything number. So as it turns out, this equation that has a line with a slope of 0 and a y-intercept of 2, that could be reported as just simply y equals 2. And if you think about what that looks like, if we have a y-intercept of 2 but a slope of 0, well, that's just a horizontal line. So if you haven't noticed that pattern already, when we have y equals some number, that's going to produce a perfectly flat and horizontal line. Now finally, 2 sets of examples here. In part A, we were just graphing these 2 slope-intercept equations. And when you were done with that, I had hoped that you recognized these 2 lines appear to meet at a 90-degree angle. And if we recall, this is this would have been indicated by looking at our slopes. If we had our slope of -1/2 and a slope of 2, think of that as negative 1 over 2 compared to positive 2 over 1, if you will. Imagine us flipping this fraction, or this fraction for that matter, and then putting a negative sign in front of one or the other. When these are flipped and one's positive and one is negative, we call those opposite, or sometimes negative, reciprocals. And I would say that opposite reciprocals, or negative reciprocals, always indicate perpendicular lines. Now, if opposite reciprocal slopes indicate perpendicular lines, what was the giveaway that we were dealing with parallel lines? Hopefully you recall there that parallel lines are found when slopes are equal. So again, when we have same slopes for linear equations, that will end up generating parallel lines. Hope this video was helpful for you and you got something out of it. If you have questions, please be prepared to ask them when I see you next. And until then, thanks for watching.